looking at the molecule shapes while building them, let's start at the top on the lab procedure, which is just two atoms bonded together. So taking two hydrogen atoms and bonding them together in two-dimensional space in the plane of the paper, you just have two hydrogen atoms, and in 3 dimensions you can see that these two hydrogen atoms are smushed together. That's the definition of a molecule, and they are showing the bond. This is a single bond. When you have two atoms bonded together, it's the simplest shape. It's 2 points on a line, which is called linear. Two atoms bonded together, like this example, is two oxygen atoms. Now oxygen, in order to fulfill the octet rule for each oxygen atom, has a double bond, and so we'll see that when I switch to the 3D. So this is the molecule, two oxygen atoms, and they're smushed together, but the ball and stick will show this is a double bond between those two oxygen atoms. Each oxygen has 8 electrons around it, and in order to achieve that, two pairs of electrons had to be shared. So there are 4 electrons represented in those two bonds in the double bond shape. When you have two atoms bonded together, whether it's a single bond or a double bond, and we'll see also a triple bond, two atoms bonded together in 3-dimensional space is still a linear shape. So here's another example of two atoms bonded. This is nitrogen, or N2. It's another molecular element like oxygen. And this in 2D is just two nitrogens. But 3-dimensional, you can see this is the nitrogen molecule, N2. And looking at the bonds here, this is a triple bond. There are 3 bonds connecting those two nitrogen atoms. And they're not going in 3 different directions. They're connecting the two atoms. And you can see that the two atoms are actually closer together for a triple bond than a single bond or a double bond. So each bond brings the two atoms closer together, but it's still in one line. It's still a linear overall shape. So this is a linear shape whether you have a single bond, double bond, or triple bond between two atoms. So two atoms is the simplest molecule shape. Let's take some molecules that have more than two atoms. So when you have carbon with two oxygens, this is carbon dioxide, CO2, and the 2D Lewis structure you have on your lab report. And let's look at the 3D. What you have here to start with is a central atom with an atom bonded on either side. So this is one central atom with 2 bonds and no lone pairs. So 1 bond, 2 bond, and no lone pairs. In 3D, you can see this is linear. So let me hold this. This is a linear shape where all those atoms, the 3 atoms, are in one line. And this is a double bond on either side of the carbon. And there are 2 double bonds, but the double bond, just like we saw before, isn't going in 2 different directions. It is a bond. So this is central atom with 2 bonds. And that is the definition of the linear shape. So here's a molecule with boron and 3 hydrogens. 1, 2, 3. The 2-dimensional Lewis structure is 3 hydrogens, and it can be on 3 of the 4 sides. It can be like here, left, top, and right, or, let's build this again, I can put left, right, and bottom, or I can put any 3 sides. So, did I do this one yet? So this is still the 2D shape is the same. Basically, I'm going to just be rotating this in the plane of the paper. The 3-dimensional shape, though, is when you have a central atom with 3 bonds and no lone pairs. So that's the trigonal planar, 3 bonds. And let's take a look at this. Is the central atom with 3 bonds, and what this forms is a trigonal planar is the name, which is basically a flat triangle. A trigonal means triangle, and in a plane, that's flat. So this, I can move this around. It's got 2 sides. You could flip it over or flip it over, all in one plane. They are not on one side or the other side. They are all just, you could line them all up if I turn it like that. Okay. This is going to be methane, which is CH4. So the 2-dimensional Lewis structure is a carbon with 4 hydrogens. So this is 4 hydrogens, 1 on each side, and this is in flat. When you convert it to 3 dimensions, though, this changes quite a bit. It turns into, this is the tetrahedral shape. So the tetrahedral shape is a central atom with 4 bonds and no lone pairs. And this is the tall pyramid I talked about in lecture. So it's a tripod with a tall top, a tall pyramid. And so you can see that you can turn this around in 3-dimensional space, and there's always going to be a base of 3, and it's equal on all sides. If you have a pyramid, you can see that you can flip it around, that there actually is no top. You can flip this around in 3-dimensional space. Getting into some of the molecules that have lone pairs on the central atom, let's build, this is an oxygen with 2 hydrogens. Now this is the 2-dimensional Lewis structure of H2O, water. And you can see that this hydrogen, oxygen, and hydrogen are all in one line. This is a linear shape in 2D. However, in 3 dimensions, the picture is different. So let's click on 3D. And you can see that this is not linear, that this is a V shape. So this is V, or I could turn it upside down V. And this is because the hydrogens get pushed downward due to there being lone pairs on the central atom, that's the red oxygen atom, that don't show up in this shape, but they affect the bonds that do show up. So these bonds would really rather space out and be linear, but they can't because lone pairs have an outsized effect, forcing the lone pairs closer together, or the lone pairs force the bonds closer together into that V shape instead of being a linear shape like we just saw, where we saw earlier the central atom with 2 bonds and no lone pairs is linear. But when you add lone pairs, either 1 or 2 lone pairs, it forces this V shape, which is called bent. Here's a structure where we have the oxygen molecule, O2, and adding a 3rd oxygen turns this into ozone, O3. Now, the 2-dimensional Lewis structure is just going to be all those oxygens in a line. But ozone is an example where the 3-dimensional VSEPR shape is quite different because the central atom, the central oxygen, has 1 lone pair and 2 bonds. That's the bent shape. So let's take a look at that. So this is that bent shape. You can see that the atoms have a single bond on one side and a double bond on the other side, but this is the same idea that it doesn't matter if it's a double bond or single bond, just 2 bonds to the central atom plus 1 lone pair lead to the bent shape. So this is the V shape, either downward V or upward V, and space filling still is a V. So this is going to be the structure of ammonia, which is NH3. So this is a nitrogen, is a central atom, and there are 3 hydrogen atoms. So the 3 hydrogen atoms can be left, bottom, and right, or left, top, and right. It doesn't matter. There are going to be 3 hydrogen atoms on the 4 sides. And so this in 2-dimensional space is not the same as its 3-dimensional. So what you have for ammonia is a central atom with 3 bonds and 1 lone pair. So if you just had a central atom with 3 bonds, that would be trigonal planar. So that would be a flat triangle. But ammonia has that lone pair which forces the 3 bonds of the hydrogens down to be a low pyramid called trigonal pyramid. So let's take a look at that. So this is the 3 bonds are forced downward. Instead of being flat, you can see they're more on one side compared to the other trigonal planar structure we saw earlier. So they're all on one side, and flipping this over, they're all on one side. So this is the flat, the low pyramid, trigonal pyramid, and this is ammonia NH3.